Hi, Cecilia. Can you hear me okay? Hello. Okay, good. All right, so uh, my video is not doing what it was supposed to do and what it did last time. So can you see a document? Is there anything that you can see, or is there just a picture of my face? Okay. All right, so I have got to get that sorted. I'm not sure what it's doing or why it's not doing that. So give me just a minute to play around with this, and then we will get started. I just need this to be able to show the video, and I don't know why it's not. Okay, what about now? Okay, all right, so now let me see if it'll let me make this bigger. It's not letting me make it bigger. It's very strange. So far, Cecilia, you are the only one. We only had one person last time as well. So this is obviously you know why you're here. This is the stats review for test number 2. This is chapter 3. Now I have a bunch of sample questions that are from the review homework online, and we can certainly just, go through all of these. Provide a good overview of, what's going to be on the test and what you guys are expected to have learned. But also, if you have specific questions that you want to go over, we can certainly do those as well. So in the interest of time, I'm going to go ahead and get started. I'm going to wait for you to type that message first, but then we'll just dive right in. Okay. All right. So number 1, use the fundamental counting principle to solve the problem. How many different codes of 4 digits are possible if the first digit must be 3, 4, or 5, and if the code may not end in 0? All right, so the fundamental counting principle, this is the one where we say we just multiply all the different options out if they're occurring in sequence. So it's a 4-digit code, so I'm going to draw 4 blank lines. This represents the first digit of the code, the second digit of the code, the third digit of the code, and the fourth digit of the code. So let me zoom in a little bit more. So we're going to go through and we're going to say, okay, how many different ways can I create that first digit, or how many different options do I have for the first digit? So it said that the first digit must be a 3, 4, or 5. Okay, 3, 4, or 5, that's only 3 options. So I only have 3 options for the first digit. I'm going to be multiplying, I should probably write that in now. I'm going to be multiplying all of these together. So I have 3 options for the first digit. The other clarification that it gave us is that the code cannot end in 0. So instead of having 10 options for this fourth digit, we only have 9 options, right? Because when we have the digits 0 through 9, that's 10 options. And I see Kendra has joined. All right, let me make sure that I'm able to let everybody in. Okay, good. All right, so Kendra, just to let you and Cecilia know, this is being recorded. And if you have any questions, you can put them in the chat, or you can do like a raise hand. And if you have a microphone, we can enable that and you can ask a question verbally. But we've just got a bunch of questions from the homework, and we're just gonna burn through them because we've only got an hour. Okay, so the first option, we only have 3 digits to choose from. The last digit of the code, we only have 9 instead of 10 because we can't use 0. And then the middle two, we do have 10. So all we're doing is plugging that into our calculator. So we're going to do 3 times 10 times 10 times 9 and we get 2,700. So that's how we get that number there. All right, moving right along. We got another fundamental counting principle. So a singer-songwriter wishes to compose a melody. Each note in the melody must be one of the 12 notes in her vocal range. How many different sequences of 3 notes are possible? So same process where we say, okay, there's the first note, the second note, and the third note, and we're going to multiply the number of options we have for each, and that will tell us how many different options we have total. Okay, so it told us that she has 12 notes in her vocal range, and it didn't say that we couldn't repeat notes or anything. So that means she could do all 12 notes for the first one, but she could repeat a note, and she could repeat it again. So we have all 12 notes for all 3 options. Again, we're going to plug that in. There's a couple different ways you could plug that in. You could say 12 times 12 times 12, or you could say 12 to the third. So you could type in 12, and then here, I'm going to move this up a little bit so you can actually see. Here, I'm going to move it maybe up here. The caret symbol right here, you can say to the, and your calculator might make it look a little bit different on the screen, but mine, it actually goes up into the exponent there, and then we say to the third. And either way, we're still getting 1,728. Okay, so that's how we're getting that answer right there. All right, moving right along. Okay, if an individual is selected at random, what is the probability that he or she has a birthday in July? And then ignore the leap years. Okay, so what we need to do here is we need to put, we're going to create a fraction, and the numerator is going to be the number of days in July. The denominator, or like our sample set, you can kind of think of it that way, is the number of days that we can choose from. So the number of days in the year. Okay, so there are, and it's saying to ignore the leap years. So there's 365 days in the year, and there are 31 days in July. So they've gone ahead and left it as a fraction and not turned it into a decimal. So just kind of a quick test taking tip. If you're, here, let me let Sean in. I don't know why it makes me admit some people and other people can just pop on in. I'm not really sure why. Hi, Sean, my name's Maxine. We're going through a bunch of questions here. This is being recorded. I just have to let everybody know that for privacy purposes. We'll make these recordings available later so that you guys can go back and look at them. So yeah, test taking tip is that if you are, super focused and you're just on a roll and you're like, great, okay, I got 31 over 365. I'm going to plug that into my calculator. And you take the time and you do that and you say, if I were to go to 3 decimal places, that's 0.085. And you're spending all that time thinking about how to turn your answer into something that they don't want you to turn it into. So always a good idea to, take a look at what your answer options are so that you don't spend unnecessary time turning it into something else. And yeah, no worries, Sean. Yeah, people are going to pop in and out. We understand that people have, busy schedules, work and school and all that. So no worries. You come in when you can. All right, next one. Okay, number 4. The distribution of blood types for 100 Americans is listed in the table. If one donor is selected at random, find the probability of selecting a person with blood type A positive or A negative. And then it gives us those numbers. All right, so that or tells us that we're going to be using the addition rule. Okay, so the addition rule says that if you have that you can find the probability of A or B by saying probability of A plus the probability of B, and then you subtract anywhere that they may overlap. So minus the probability of A and B. So sometimes when you're doing this, there isn't going to be an overlap, and sometimes there is. But just remember that that's the whole thing. This is the probability of A. I should probably write that out. The probability of A or B is this. Okay, so we are going to find the probability of A positive. We're going to add that to the probability of A negative, and then we are going to subtract any overlap. But we take a look at this and we see, well, there is no overlap, right? You can't have both A positive and A negative blood. So we're not going to need to subtract where they overlap. All right, so A positive blood. So if one is selected random, find the probability of, yeah. Okay, so we have I just realized when I when I went through my notes and did this ahead of time that I wrote this out differently. But anyway, so we have what we're going to do is we are going to. Oh no, I didn't, because we have 100. So these people are out of 100. So there's a couple ways you can write this out. So A positive people are right here. That's 34 out of 100. But in my notes when I did this, I just immediately wrote it out as 0.34. So if you can do that in your head, great. But if not, go ahead and write out over the fraction of 100. So kind of like, you know how you guys do like the part over the whole, right? That's what fractions are. This is your sample set. This is how many people were surveyed or were, blood was taken from them. That is your sample set. That's how many people you have to choose from. This is how many people were that particular one. So you're creating the part over the whole, which creates the decimal. But if you want to jump right to this, you can. All right, but either way, to that we are adding A negative. So I have 6 people out of 100, which is going to give me 0.06. Again, you can plug that into your calculator if you want to, if you're not feeling super confident with, your decimals and fractions and all that. But either way, when you go to add these up, that's going to give you 0.4. Okay. All right. Moving on to number 5. Okay, distribution of master's degrees conferred by a university is listed in the table. What is the probability that a randomly selected student graduating with a master's degree has a major in engineering, and then round your answer to 3 decimal places? Okay, so the first thing that we need to do is to say, well, what is my sample set? How many degrees do I have in total? I need to find the sum of the frequencies, right? That notation should look familiar from the last couple of chapters. So we're going to add all of these up, right? So we're going to go 216 plus 207, whoops, 216 plus 207 plus 67 plus 176 plus 222, and we get 888. So there were 888 total master's degrees conferred by this university. So that is our sample set. So that is our denominator, right? So what we're going to have here is in the numerator, we're going to have what they're asking for. They're asking for a major in engineering. So we're going to have the number of engineering degrees conferred over the number of all the degrees, or the total of them. Okay, so engineering, 67. So we have 67. Oh, can't really see that. We have 67 over 888. So we're going to plug that into our calculator. And we get a decimal, and it told us to go to 3 decimal places. Let's move this paper over a little bit here. There we go. So we have 075450450, so on and so on. 3 decimal places is 075. Okay. Right, the part over the whole, the sample set goes here. What they're asking for goes in the numerator. All right, moving on. Okay, number 6. Explain why the statement is incorrect. The probability of rain tomorrow is 136%. What makes the statement incorrect? All right, so when we're working with probabilities, we have to keep in mind that the probability of an event, event A, is always going to be between 0 and 1, right? Can't be any less than 0, can't be any more than 1. If it is 0, that means that the event is never going to happen, or you can think of it as the event is impossible, but there is a 0% chance that it will happen. Whereas if it is 1 or 100%, then the event is certain. Okay. So they've given us a probability that's more than 1. The probability of an event cannot exceed 100%. They could say that it is 100% going to rain tomorrow. That's always a risk of giving percentages when talking about weather, but they could say that, but they couldn't say any more than 100%. Always has to be between 0 and 1, inclusive. Inclusive meaning it's allowed to be 0 and it's allowed to be 1, but it can't go beyond that in either direction. All right. Okay, number 7. The probability that an event will happen is probability of E equals 0.44. Find the probability that the event will not happen. Okay, so what they're talking about here is the complement of the event. So the complement of the event is 1 minus the probability. Either it's going to happen or it's not. So if they said the probability that it's going to happen is this, then 1 minus that will give us the probability that it won't happen. Because both of the probabilities together, the probability that it will happen and the probability that it won't happen, together have to add up to 1. They have to equal 1. Right? So if I said there's a 30% chance that it's going to rain tomorrow, then I would also need to say that there's a 70% chance that it won't rain tomorrow, because 70% plus 30% is 100%. So oftentimes when we're talking about probability, it can be easier to find the complement of the thing you're looking for and then subtract it from 1. So that's something that we do quite a bit. So we don't even know what this event is. All we know is that its probability is 0.44. So the complement of it, or the probability that it won't happen, is 1 minus that. So 1 minus 0.44 is 0.56. Okay. All right. I know I'm going kind of fast, but we got a lot of problems to get through, and I want to make sure that we cover them all. And also, if you guys do have questions, I'm hoping that we might have time for that at the end. Last session I went over by quite a bit, but I do not have time to do that today. So we really got to keep to our 1 hour. Okay, number 8. The frequency distribution to the right shows the number of voters in millions according to age. Consider the event below. Can it be considered unusual? A voter chosen at random is between 35 and 44 years old. Okay, so let's take a look at what they're actually asking us. This 35 to 44. They want to know, is this unusual? So for something to be unusual, it needs to have a probability that is 5% or less. So 0.05 or less. So the probability that event A is unusual, or sorry, not the probability that it is unusual, but if the probability of A is less than or equal to 0.05, then we would say that it is unusual. Okay. Real quick, before we dive into these exact numbers, we talked already about probabilities going between 0 and 1, right? So 0 is never, 1 is certain. And as we go closer to 0, it's becoming more and more unusual. As we get closer to 1, it's becoming more and more common, right? Does that make sense? So the sort of barrier number for being actually called unusual is 0.05. Okay, so we need to actually calculate the probability of what they're asking us for, that a voter chosen at random is between 35 and 44 years old, and say, okay, is that less than or equal to 0.05? So how do we do that? We are going to say that we need to do this number over the full sample set, right? So we need to add all of these up. So we're going to do that on our calculator here. 11.8, 10.8, 24.6, 26.6. Whoops. Oh no. I have fat fingers. Sometimes I hit the wrong button. Okay, so our sum here is 148.4. That's the sum of our frequencies. So that's the number that's going to go in our denominator, okay? 148.4. And what's going in our numerator is this particular frequency, that a voter is between 35 and 44. So that's 26.9. So we can say 26.9 divided by, and I don't know how comfortable you guys are with your calculators, but if you didn't know already, you could go ahead and write in 148.4, but a tool that can be useful is to just have the calculator take the last answer that you did and plug it in there. So on the calculator, all the way down here, on mine it's above the negative symbol is answer. So because it's above it, you can hit second answer, and it'll take the answer that you previously had and plug it in there. Okay, so that's how we're getting that it is about 0.181. Okay, so if we're saying that the probability of this event is about 0.181, is that less than or equal to 0.05? Is it close to 0? No, it's not. So that's why it's not unusual, because it's not less than or equal to 0.5, right? If we're 0.0, I'm not 0.5, 0.05. If we're at 0.05, we're really close to 0. We're over here. 0.5 or 50% is right in the middle, but 0.05 is really close over here, right? 0%, 50%, 100%, 5%, right? Okay, so that's why, no, it's not unusual, because it's not less, specifically, it's not less than or equal to 0.05. Okay. Number 9. Classify the events as dependent or independent. Event A, a red candy is selected from a package with 30 colored candies and eaten. Event B, a blue candy is selected from the same package and eaten. Okay, so there's a few ways you can think about this. One way is to just kind of think it through and say, well, does one affect the other, right? Because if they are dependent, one will affect the other. If they are independent, they will not. Another way is to actually follow the sort of the rule. Okay, so if the probability of event B is exactly the same as the probability of event B given event A, right? Remember, that's how we read this, the probability of B given A, then they are independent. But if the probability of event B is not equal to the probability of B given A, then they are dependent. Okay. So first, we're just going to kind of think about this sort of theoretically, and then we're going to assign some numbers to it so that we can actually do some calculations if we wanted to. Okay, so if I have 30 candies and I pull a red one and I eat it, if I then go to calculate a blue candy, given that I had a red candy, I now have less candies. I don't have 30 candies anymore. I have 29 candies. So if I do event A, it affects what happens in event B, because instead of having a solution set of 30 candies, I only have a solution set, or I'm sorry, not a solution set, but a sample set of 29 candies. So event B is affected by event A. Okay, but again, let's assign some numbers here. Let's say that there's 20 red candies and 10 blue. So if we were to actually calculate this, we would say, okay, a red candy is selected from the package with 30 colored candies and eaten. A blue candy is selected and eaten. So, so this is A, right? And this is B. So if we ignore A and just calculate B, okay, so B, a blue candy is selected from a package and eaten. So that would be 10 out of 30. Okay, so that's going to give us 0.3 repeating. Okay, that's the probability of just B. But the probability of B given A, if I pull a red candy, instead of having 30 candies to choose from, I only have 29 to choose from. Now, 10 of them are blue, but I am now at 10 out of 29, which I mean, I could do the math and plug it in, but we can see that these are different fractions, right? It's 0.345 approximately. So these are different. So these are not equal, which means they are dependent. So if you're having trouble thinking about it theoretically, if you have actual numbers that you can use, you can go ahead and actually do the calculation. Depending on the problem, it might be easier to just think about the theoretics of it, and it might be easier to actually do this calculation. Just depends on the problem. All right. Okay, number 10. Group of students were asked if they carry a credit card. The responses are listed in the table. If a student is selected at random, find the probability that he or she owns a credit card given that the student is a sophomore. Okay, so when you have one set up like this, the given, that becomes your solution set. So it's like, or I keep saying solution set, I apologize. I mean sample set. So if we're given that it's a sophomore, then we're only looking at the sophomores. That's all we can look at. We have to assume that it is a sophomore because it is given that it is a sophomore. So instead of our denominator being all the totals, our denominator is only the total number of sophomores because that is what we are given, right? So the given becomes the sample space. Okay, all right. And then what specifically is it asking for? That they own a credit card. All right, so they are a credit card carrier versus not a credit card carrier. Okay, they are a credit card carrier, but we're only allowed to look at where credit card carrier and sophomore overlap, right? Because we're only allowed to look at the sophomores. So the number of credit card carrier sophomores. Okay, so that's going to be 34 over 40, right? The given becomes our denominator, and then the numerator is where it overlaps with the given. Okay, so again, you just plug this into our calculator, 34 over 40, and that's how we're getting the 0.85. Okay. All right, on to the next. 11. what is the difference between independent and dependent events? So this is just a definition one. So make sure that you've kind of got these sorted in your head, right? Two events are independent. We kind of already went over this. When the occurrence of one event does not affect the probability of the occurrence of the other event, but two events are dependent when the occurrence of one event does affect the probability of the occurrence of the other event. So, if I pull a candy from the bowl, then that affects my ability, or not ability, but it affects the probability of pulling a different candy from the bowl because there are now fewer candies in the bowl. Okay. All right, number 12. So for this one, I have written out the survey results twice so that we can actually mark on them for both parts of this question. All right, so the accompanying table, so these tables are the same is what I'm saying. I just rewrote them or copied them twice so that we could look at the problem 2 times for part A and part B. The accompanying table shows the results of a survey in which 250 male and 250 female workers ages 25 to 64 were asked if they contribute to a retirement savings plan at work. Complete parts A and B below. All right, A, find the probability that a randomly selected worker contributes to a retirement savings plan at work given that the worker is male, right? So the given, that is all that we are looking at. We're only looking at that. That's our denominator. Our denominator is the given. Okay? In the numerator, they want that they do contribute to a retirement savings plan. So they do contribute. So, this is what we're looking at, but we're only allowed to put in where they overlap, right? So we have 118 is the number of males who contribute. That's what goes in the numerator, the number of males who contribute. The denominator is what our given total is. So that's how we're getting the 118 over the 250, which if we plug in, that's how we're getting the 0.472. Okay, so now we're going to do the same process with the next one. For part B, they want find the probability that a random selected worker is female, given that the worker contributes to a retirement savings plan. So the given is that they contribute. That total is our denominator. The given is that they contribute. So the numerator is going to be where this and the given overlap. So where do female and the given overlap? 150. And I encourage you to mark up your papers, to kind of help you see this. If you've got highlighters, that can be a good way to do that, right? You can highlight female, highlight contribute. Where did you highlight twice? The overlap, that's your numerator. Again, the given, the total of the given, that's your, total of the given. For this one, it was this. That's your denominator. For this one, the total of the given was over here. For this, the given was here. Okay. All right. Okay, number 13. So again, another kind of independent, dependent sort of definition test here. For the given pair of events, classify the two events as independent or dependent. Right? So flipping a fair coin and getting tails, flipping the same coin again and getting heads. So the two events are independent because the occurrence of one does not affect the probability of the occurrence of the other. So somewhere in the book, it says something about how people kind of get confused on this because they think, oh, well, it's supposed to be 50-50, so I've got less of a chance the next time, right? But this is an inanimate object that doesn't know what it flipped last, right? I think it's called the law of large numbers says that, the more often you do this this event, the flipping, the closer it's going to get to that probability of 0.5 of getting either heads or tails. But you have to do it a ton of times for that to happen. If you just do it twice, you may twice in a row get the same thing, right? The coin doesn't know what it flipped last. So they're independent because the coin is not keeping track of what it flipped on last and trying to stay at 50%. All right. Okay, number 14. 2 cards are selected from a standard deck of 52 playing cards. The first card is not replaced before the second card is selected. Find the probability of selecting a jack and then selecting a 6. Okay, so what we have here, first of all, I sort of copied and pasted this here so that we can kind of keep track of what we have here. So hearts and diamonds are red, spades and clubs are black. I feel like a lot of people know this, but some people do not. So if you don't, make sure that you kind of understand this, because they're going to assume that you know how many cards are in each. Also, face cards are the king, queen, jack. The ace is not a face card, so you might run into that as well. Okay, so this is saying find the probability of selecting a jack and then selecting a 6. So let's start with the probability of selecting a jack. So there are 52 cards in a deck. That's how many we have to pull from. We're going to start with how many of them are jacks. So we have 1 of each in these columns. So that's 4 out of a 52. Right? So what we're using here is the multiplication rule. Okay. These events are dependent. So let me write this out real quick. Multiplication rule. When you have dependent events, so we have the probability of A and B, you do the probability of A times the probability of B given A. Right, that's what we're writing out here. Okay, so this is the first. This is the probability that we pull a jack. Then we have to do the probability of selecting a 6 after we pulled the jack, right? So we don't have 52 cards anymore, right? The first card is not replaced. Instead of having 52 cards, we only have 51 cards. Okay, all right, we pulled a jack. It's asking us to then select a 6. So there were 4 6s to choose from, right? 1 in each suit here. Us pulling a jack didn't affect how many 6s there were. It's not like we pulled one of these 6s. So we still have 4 of the 6s to choose from. Okay. We're going to multiply these two together, and that's going to give us our probability. So 4 out of 52 times 4 out of 51, and we get 0.006. Okay. Okay, so the probability of A and B, we do the probability of A, and we multiply it by the probability of B given that A occurred. Right. Okay. All right, moving on to 15. Okay, so this might be a weird question, but will we be allowed to have a chart of the cards during the test? I don't know about cards, and it was really hard for me to try and complete those exercises without looking at the chart of the cards. I don't know, but I don't believe so. So I think just to be safe, maybe take some time and kind of, I don't want to say memorize, but just kind of make sure that you understand. So there's 52 cards in a deck. Sometimes they'll remind you that 52 is the number of cards in a deck. Half of the deck is red, half of it is black. There are 2 red suits and there are 2 black suits. And a quarter of the deck is each of the suits. And then in each you go from 2 to 10. And then you have Jack, Queen, King, and then Ace. So I would say take some time to look at that and make sure that you kind of could create that if you needed to, because they might need you to already know that. in the same way that they would say, like, oh, you flip a coin, what's the probability that it's heads? They need you to know that a coin has heads on one side, tails on the other. But yeah, a lot of people are not super familiar with the cards, so don't feel bad about that. Not a weird question at all, but you do need to get familiar with it. So good question. Okay, number 15. Patient has a 59% chance of surviving bypass surgery after a heart attack. If the patient survives the surgery, then the patient has a 70% chance of making a full recovery. Find the probability that the patient survives surgery but does not make a recovery. Okay, so we have the probability that they survive the bypass surgery. Okay, so that's the first thing. If the patient survives the surgery, or sorry, find the probability that the patient survives but does not make a full recovery. Okay, so we're going to say probability that they survive and the probability that they don't recover. Right, those are the two things we're multiplying. Okay, the probability that they survive the surgery is 0.59. Okay. Then it says the probability that they don't recover. Well, we weren't given that, were we? Instead, we were given the probability that after the surgery that they do make a full recovery. Okay. So what we have to do here is we have to calculate the complement. Right? We talked about this before, the 1 minus, right? So 1 minus the probability of making a full recovery is the probability of not making a full recovery. I didn't mean to get so close to that. All right, so we need to find the probability of not making a full recovery. So we're going to do 1 minus the probability of making a full recovery. Probability of not making a full recovery is 0.3. That's what we're putting here. 0.3, or you could say 0.30. That's what we're putting there. That's what we are going to need to multiply. So again, it's asking if the patient survives, or sorry, find the probability that the patient survives the surgery and then doesn't recover. So we're going to multiply those two together. They gave us this. In order to find this, we had to find the complement of what it gave us. So plug that in. And that's how we're getting the 0.177. Okay. All right. Number 16. Decide if the events A and B are mutually exclusive or not mutually exclusive. A person is selected at random. Their birthday is in the fall. Their birthday is in October. So mutually exclusive events cannot both occur, right? That's the definition. That if things are mutually exclusive, events cannot both occur. Right? They exclude each other. They mutually exclude each other. They are mutually exclusive if they can't both occur at the same time. So is it possible for both of these events to occur at the same time? Can I have a birthday in October and a birthday in the fall? Yes, because October overlaps with the fall. Now, certainly I can have a birthday that's in fall, but that's not in October, right? Fall starts, what, September 22nd? So I can have something that is in the fall, but that's not in October, but I can have something that overlaps. I can overlap. I am allowed to overlap. So they are not mutually exclusive, because mutually exclusive means you can't overlap. Okay. Okay, I'm going to try and speed things up just a little bit. I'm going a little slower than I wanted to be going. All right, number 17, the table lists the smoking habits of a group of college students. If a student is chosen at random, find the probability of getting someone who is a man or a woman. Round your answer to 3 decimal places. All right, so there's 2 ways to think of this. We can just just start right in on the math, or we can think about it theoretically. So if we just started in on the math, they said a man or a woman. So a man would be 203 out of the total of 421, or means we're going to add these together, right? A woman would be 218 over the total of 421, and we would add those up and we would realize, oh, hey, that's a 1. That's because in this group of students, they had to categorize them as either man or woman. So both of those categories together have to equal the total. So it has to equal 1. Okay? It's like if I gave you, a bowl of candy and there's only red and blue in it. And I said, well, what's the probability of choosing, either a red or a blue? 1, because that's both things that are in it. That's all that we have available. But again, if you're not thinking of it in that sort of theoretical sense, you can go ahead and do the math and you will still get the answer. Also, we add them up and then we subtract where they overlap. And here there is no overlap between man and woman. All right, number 18. There we go. Distribution of a master's degree conferred by a university listed in the table. Assume the student majors in only one subject. All right, what's the probability that a randomly selected student with a master's degree majored in business, education, or engineering? And then round your decimal to 3 places. So the first thing that we have to do is we have to find the sum of the frequencies. We have to say, okay, how many students were asked? So for the purposes of time, I'm not going to plug that into my calculator. But if we did plug it in, we would get 904, right? That's our sample space here. So with the addition rule, when you have 3 things, in addition to adding them together, you also have to subtract where they overlap and then add back in where all 3 of them overlap. Now, this question, it doesn't apply because there's not overlap, but real quick, I'm going to show you kind of just like the little top bit here. The addition rule, when you have 3 events, can you see yeah, there you go. You have to add the 3 events together, then you have to subtract what you counted twice, right? Because we can't count sections twice. So think of it as a Venn diagram here. We have A, B, and C. Let me zoom in a little bit. Right? So if I count all of A and all of B and all of C, well, those overlapped sections I've counted more than once. So I need to go ahead and get rid of those. So I'm going to get rid of where A and B overlap, and I'm going to get rid of where A and C overlap, and then I'm going to get rid of where B and C overlap. But then I need to make sure that I add back in that very center part because I subtracted it too many times and I wasn't counting it. So I do have to add in where all 3 of them overlap. Now, this particular question, we don't have to do all of that because they don't overlap at all. But I think it's important that you guys are aware of that because you might get a question where they do have some overlap. Okay. But for this one, we just have these 3 things. The business, okay, business was, I can think of it that way, 171 over the total. And to that, we're going to add education, which is the 219 over the 904. And to that, we're going to add the engineering, which is the 91 over the 904. Okay, we're going to add all those up and turn it into a decimal, and that's how we get that. Quick side note, you'll notice that there's 3 things that we added together. If we wanted to, potentially, it might save us some time if we actually found the complement. I mean, this is getting a little fancy, but we could have added these 2 together and then done 1 minus that probability. That's only if you're feeling fancy. All right. Okay, number 19. Of the cartons produced by a company, 5% have a puncture, 8% have a smashed corner, and 0.6% have both a puncture and a smashed corner. Find the probability that a randomly selected carton has a puncture or a smashed corner. Okay, so remember, or, we're using the addition rule, right? Sorry, you couldn't actually see the question. Right, so this is the addition rule. Okay, so the addition rule says that the probability of A or B is the probability of A plus the probability of B, and then you have to subtract what you counted twice, the probability of A and B, where they overlap, right? So that's what we're going to do. So that a randomly selected carton has a puncture. Okay, they said that's 5%, so that's 0.05. Okay, or a smashed corner, so that's our B. The smashed corner, that's 8%, so that's 0.08. But then we have to subtract where they overlap. Which cartons have both? Which cartons both have a puncture and a smashed corner? That's 0.6%. So just be careful with your decimals here, that's 0.006. Okay, so we're going to add these up and then subtract where they overlap, and that's how we're getting our 12.4. Okay, just again, be careful with your decimals here. You don't want to accidentally put a 0.06 because that would be 6%, and it's not. It's 0.6%. Okay. All right. We got another card one. Number 20. Card is selected at random from a standard deck. Find the probability of each event. So we're doing this 3 different times. All right, randomly selecting a heart or an ace. Okay, so we're gonna do these. So again, we're using that addition rule, right? So we're doing the probability of A plus the probability of B minus the probability that they overlap, all right? So a heart or an ace. So we're going to start with a heart. So the probability of selecting a heart, there are, this up here, zoom back a little bit. You can see the whole thing. You still can't see the whole thing. I don't want it to be too small there. Oh my gosh, you still can't see the whole thing. Okay, now you can see the whole thing, right? Sorry, I don't have a very big desktop space to work with here. Okay, so the probability of a heart or an ace. So let's start with the heart. There are 13 hearts. So 13 out of 52, okay? Or an ace. So how many aces are there? There are 4 aces out of 52. But we do have to subtract where they overlap. So how many hearts that are aces exist? So here were all of the aces, here were all of the hearts. There is only 1 ace of hearts. So we subtract 1 out of the 52 cards. Okay, the probability of A plus the probability of B minus the probability of A and B, or of where they overlap. If you add those together in your calculator, or add and then subtract, that's how you're getting the 0.308. I'm not going to plug that in just for the purposes of time. Okay, next one. Probability of randomly selecting a black suit or a 7. All right, so black suits. So half of the deck is black. So that's 26 out of 52 because half the deck is black. Or a 7. How many 7s are there? There are 4 7s. So 4 out of 52. Now I have to subtract where black suits and 7 overlap. So how many black suits are 7s, or how many 7s are black suits? So there's 4 7s and 2 of them are black suits. So minus 2 over 52. Okay. Right, and then the last one, the probability of randomly selecting a 5 or a face card. So we have 5, so there's 4 of those, 4 out of 52. A face card. So again, a reminder, an ace is not considered a face card. It's only the king, queen, and jack that are the face cards. So we have 3, 6, 9, 12 face cards. And then we would subtract where they overlap. Well, face cards don't overlap at all with 5s. So if you wanted to, you could actually write out minus 0 over 52, but you probably wouldn't do that if you were on a test. Right? Okay, we're getting to the end. We're going to get through all these questions. Right, number 21. Decide if the situation involves permutations, combinations, or neither. Explain your reasoning. The number of ways 11 people can line up in a row for tickets. Okay, so remember the definitions here. Right? Permutations, the order matters. It matters. It is important. I care if I come in first in a race versus fifth. But a combination, the order doesn't matter. Which is why a combination lock is misleading, because the order that you put those numbers in actually matters. So, yeah. So, how many ways can they line up in a row for concert tickets? It's a permutation because the order matters. Right? Am I going to be first in line or am I going to be last in line? Maybe I don't get a ticket because I'm last in line. Right? Okay. All right, number 22. Determine whether the following problem involves a permutation or a combination and explain your answer. How many different 7-letter passwords can be formed from the following letters if no repetition of letters is allowed? So it's a permutation because the order in which the letters are selected does matter. When you have a password, the order matters. Right? It said it was a password, so the order matters. Number 23, you have 9 different video games. How many different ways can you arrange the games side by side on a shelf? Okay, so there's the fastest way to do this is just going to be 9 factorial. Right, so remember that the exclamation mark means factorial. You could also say that, okay, I have 9 places for them to go. 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 options for the first one. After I put that first one in, I only have 8 left to choose from. After I put that one in, I only have 7 left to choose from, and so on and so forth. 3, 2, 1. And that's what 9 factorial means anyway. So in your calculator, yours might look a little different than mine, but you're going to type in your number. You're going to go to math. You're going to arrow over to probability. And then number 4, on mine, it's number 4, is the exclamation mark, which is factorial. Right? And that's how we're getting 362,880. Okay? Because you don't want to have to plug in 9 times 8 times 7 times 6, blah, 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 blah. You're going to have problems where this number is way too big for you to do that. So make sure you know how to find the factorial button on your calculator. All right, number 24, there are 43 runners in a race. How many ways can the runners finish first, second, and third? All right, so let's talk about the different ways that we can do this. So we have first, second, and third. Right, first place, second place, third place. All right, there's 43 runners. So there's 43 potentials for first place. But once that person is first place, they can't also be second place. So there's only 42 options for second place. And then once you have first and second place set, there's only 41 options for third. Okay, so if we plug that in, 43 times 42 times 41, we get this 74,046. Right, that's one way you could do it. Another way you could do it is by saying this is a permutation, so we're going to do 43 P3. Right? So in your calculator, you're going to do 43. You're going to go to math. You're going to go over to probability where we had our factorial, and you'll notice you have NPR and NCR. This is a permutation, order matters, so we're using the P. And then you tell it how many of them you're choosing. So you have a sample set of 43, and we're going to choose 3 of them, and we're telling it order matters by choosing the P for permutation rather than the C for combination. And we get the same thing. Now, you could also use the formula. I think most of your professors are not having you guys do the formula by hand of n factorial over n minus r factorial. I don't think you're required to do that by hand, but if you were, you'd have 43 factorial over 43 minus 3 factorial. We're not going to go through that because I think all your professors are just expecting you guys to do that in the calculator. Okay. All right, so that's 24. All right, I know we're at 11, but we only have a few more problems to go. So I'm going to burn through these really quick just so that we can make sure we covered all of these. If you have any questions, start typing them now so that they're typed in by the time that that I finish up with these next, let's see, we only have 28 problems. So we only have 4 more to go. Okay, 25. There are 12 finalists in a singing competition. Top 6 singers receive prizes. How many ways can the singers finish first through 6th? So order matters. There are 12 finalists and the order matters, and we're choosing 6 of them. So when we plug that into the calculator, again, you go 12, then you're going to go math, you're going to arrow over to probability, and you're going to select NPR, and you plug in how many of them you're choosing, right? That's how you're getting that number. Or if you were wanting to do it by hand, sorry, 6th. I was thinking the first 3. Excuse me. So you would do, 12, 11, 10, 9, 8, 7. This is going to be faster, right? Okay. Number 26. Excuse me. In order to conduct an experiment, 4 subjects are randomly selected from a group of 42 subjects. How many different groups of 4 subjects are possible? All right, so if I have a test group, do I care what order they're in? No, I'm selecting them for a group. I'm not putting them in any particular order. So this is a combination, right? Order does not matter. So there were 42 people to choose from, and we are going to choose 4 of them, and we don't care about the order. So that's 42, choose 4. And again, if you plug that in, you're going to get that number right there. Number 27, class has 27 students. In how many different ways can 6 of them form a group for an activity? Assume the order of students is not important. Not important, that's a combination, not a permutation. So 27 students, and we're going to choose 6 of them. 27 choose 6. We plug that into the calculator, and that's how we get that number right there. And last question is number 28. Certain lottery has 25 numbers. How many different ways can 4 of the numbers be selected? Order is not important. Again, not important means it is a combination. So there are 25 numbers to choose from, and we are choosing 4 of them. Okay. All right, so I know we said we were just going to do those, but I'm only 4 minutes over, so I actually do want to do one more problem that's a bit more complicated than what was on the homework here. Let me just pull this from my notes. Because it was a different type of problem, and just in case you guys come up against that, I wanted to include it. Okay, so actually there were 2 different ones that I thought were good examples of this. So okay, so it's a card one. So the problem said that if you were dealt, so different problem here. So if you're dealt I'm sorry, the probability of being dealt 5 diamonds, that's a diamond, apparently, from a deck that has 2 jokers. So a joker is a wild card that can represent any card, okay? So they want the probability that you are being dealt 5 diamonds from a deck that also has, in addition to the 52 cards, it's actually got 2 extra jokers. So there's actually 54 cards. Okay, so what we're going to do is we're going to have the different ways that I can have. Um, so I'm going to email the recording once it is created. I think it usually takes a few minutes, maybe an hour or so to be available. And then I'm going to email it to Professor Repnick. She is the stats coordinator, and she disseminates that out to the professors. But what I can do is I can also email the recording to all of you guys directly if you put your email in when you entered the chat. So if you didn't put your email in and you feel comfortable just typing it in a message there, then I will do that. If you don't want to type it in the message there, then you can email me directly. I will, let me put real quick, let me put my email in here. So my email address is state.edu. So I know that's confusing because it says Brandy. That's my first name. I go by Maxine, which is my middle name. So if you're going to email me, you can email brandy.horn@daytonastate.edu. Just email me and say, hey, I want a recording, and I'll send it to you directly. Okay, so we're gonna write out all the different ways that we can have 5 diamonds. Okay, so one way that we can have 5 diamonds is we can have 5 diamonds and 0. I'm just going to use J for jokers. Okay, that's one way that we can have 5 diamonds. Or we could have 4 diamonds and we could have 1 joker. Or we could have 3 diamonds and 2 jokers. Okay, those are all the different ways that I can pull 5 diamonds if I can count a joker as a diamond and I have 2 jokers available. But they're asking for probability, so that needs to go over the number of ways that I can pull 5 cards. So the number of possible 5 card hands. Okay. All right. So for this, we're going to do, how do I pull 5 diamonds? Well, how many diamonds are there in a deck? There's 13, and I'm going to choose 5 of them. Right? That's this right here. Is 13 choose 5? That's how I can get 5 diamonds. So I'm going to multiply that by, how can I get 0 jokers? Well, really, there's only 2 jokers, and I want to choose 0 of them. So this is really just 1. If you plug that into your calculator, 2 choose 0, it's just 1. So it's just 1 times this. All right, the 4 diamonds and 1 joker. So how can I pull 4 diamonds? Well, there's 13 diamonds to choose from, but I'm only going to pull 4 of them. And then how can I pull 1 joker? Well, there's 2 jokers to choose from, and I'm going to pull 1 of them. Okay. We're going to add that to, all right, 3 diamonds. So there's 13 diamonds to choose from, and I'm going to choose 3 of them. And I'm going to multiply that by, how can I choose 2 jokers? There's 2 jokers, and I'm going to choose both of them. Okay, and all of that is over the number of possible ways that I can have a 5 card hand or pull 5 cards from the deck. There's not 52 cards in the deck, there's 54 cards because we added the 2 jokers, and we're going to choose 5 of them. So you would just have to be really careful when you plug this into the calculator. Maybe do all of this first and then hit enter, and then do divided by, and then you can plug this in. So just be careful with your order of operations when you're plugging stuff into the calculator. All right. Okay. Well, thank you guys for your patience. I know we went over on time, but you can, as we talked about, the recording is going to be available. Also, you can go into any of the academic support centers when they are open to get help for statistics. You can certainly reach out to your instructor during their office hours. Also, we have an online chat available, which is often available later than the physical ASC locations are open. So that's available 8 a.m. to 7:30 p.m. Monday through Thursday, and then 8 to 5 on Fridays. So if you're at home working on this, you can access a tutor via the chat, just on the ASC's website. Also on Saturdays, The Academic Sports Center that's in Building 115 in Daytona is open. They're open from 8 a.m. to 4 p.m. on Saturdays. So you can go in and get help on Saturdays as well. Feel free to reach out to me. You have my email address there. If you have, any questions or concerns or anything, and don't hesitate to reach out to your instructor as well. They're happy to help you guys out. They like when people actually are interested in the course and are trying. So they're happy to help, and so is everybody at the Academic Support Center. So all right, well, thank you guys so much. I hope that this was helpful, and good luck on your test. All right. Oh, I'm going to wait until I think somebody was typing something. Oh, you were just saying thank you. You're welcome. My pleasure. All right. Y'all have a good day. Bye.